Hello, students. Imagine lighting a candle. The wax burns slowly, producing a steady flame. Have you ever wondered why molecules like wax or sugar don't just explode like gunpowder, even though they contain carbon, hydrogen, and oxygen? The answer lies in the type of bond holding their atoms together, the covalent bond. Unlike electrovalent or ionic bonds, where electrons are transferred, covalent bonds involve sharing of electrons. Two atoms come together and pool their valence electrons so that both can achieve a stable noble gas configuration. This bond is typical in nonmetals like hydrogen, oxygen, nitrogen, and chlorine. Whenever you see a dash between atoms, like H-H, it represents a shared pair of electrons. As we move ahead, you will see how simple sharing of electrons can give rise to an incredible variety of stable molecules. Let's begin with hydrogen, the simplest element. Each hydrogen atom has only one electron. Alone, it is unstable because it wants to complete its duplet. But when two hydrogen atoms come close, they share one electron each, forming a single covalent bond. This creates the hydrogen molecule, written as H:H. Now look at chlorine. Each chlorine atom has 7 valence electrons. By sharing one electron each, two chlorine atoms achieve an octet. The result is the Cl2 molecule, shown as Cl:(Cl). Both hydrogen and chlorine exist as diatomic gases, held together by single covalent bonds. These are examples of nonpolar covalent molecules because the sharing of electrons is equal. This simple sharing is the reason why hydrogen gas fuels rockets and why chlorine gas is used for disinfection. Now let's step into stronger bonds. Oxygen has 6 valence electrons. When two oxygen atoms share two electron pairs, they form a double bond, written as O double bond O. This makes the oxygen molecule stable with an octet. Similarly, nitrogen, with 5 valence electrons, shares 3 pairs of electrons, creating a triple bond. This N triple bond N is one of the strongest bonds in chemistry. That's why nitrogen gas, which makes up about 78% of our atmosphere, is so unreactive under normal conditions. Only under extreme conditions, like in the Haber process where nitrogen reacts with hydrogen to form ammonia, can this triple bond be broken. These multiple bonds not only explain stability but also affect physical properties like bond strength and bond length. Water and ammonia are fascinating examples of covalent bonding. In water, oxygen has 6 valence electrons. By sharing one electron with each hydrogen atom, oxygen forms two O-H bonds, resulting in the familiar H-O-H structure. In ammonia, nitrogen has 5 valence electrons. It shares 3 of them with 3 hydrogens, forming 3 N-H bonds, leaving one lone pair on nitrogen. Now here's something interesting. Both water and ammonia are polar covalent molecules. This means the shared electrons are not equally shared. Oxygen and nitrogen pull the electrons slightly more, giving rise to partial charges. This polarity explains why water dissolves so many substances, earning its title of the universal solvent, and why ammonia is used as a cleaning agent and an important base in industry. Carbon is truly special because it has 4 valence electrons. In methane, carbon shares one electron each with 4 hydrogen atoms, forming 4 strong C-H bonds. The result is a perfectly symmetrical tetrahedral molecule. Now consider carbon tetrachloride. Here, carbon shares 4 electrons with 4 chlorine atoms, giving 4 C-Cl bonds. Although each bond is polar due to chlorine's higher electronegativity, the overall tetrahedral symmetry makes CCl4 a nonpolar molecule. Both methane and carbon tetrachloride are important in daily life. Methane is the main component of natural gas and a fuel source, while carbon tetrachloride was once used in fire extinguishers and dry cleaning, though it is now restricted due to environmental concerns. These examples show how carbon's ability to share electrons creates the foundation of organic chemistry. Let's quickly revise what we've learned today. Covalent bonds are formed by the sharing of electrons, unlike ionic bonds where electrons are transferred. Hydrogen and chlorine form single covalent bonds, oxygen forms a double bond, and nitrogen forms a triple bond, explaining their stability. Water and ammonia are classic polar covalent molecules, which makes them so important in chemistry and in life. Methane and carbon tetrachloride show us how carbon builds versatile covalent frameworks that form the backbone of organic chemistry. So, the next time you drink a glass of water, breathe in nitrogen rich air, or use natural gas for cooking, remember, it's all covalent bonding at work. I hope now you can see how sharing of electrons explains the behavior of molecules all around us. In the next session, we will dive even deeper into bonding theories. Until then, keep exploring the invisible forces that shape the visible world.